Geometry Calculus section on math induction proofs. There's two ways we've been writing these different sequences. Explicit, we can get to the nth term right away. Then there's the recursive equation where we have an initial term and then how we get from one term to the next. And like a recursive equation, there's two parts to a math induction proof. We want to do the basis, that's when we show that it works for the first term. And then there's the induction step that we show that it works for each successive step. So if the k term works, then we know the k plus 1 term is going to work. Think about it like climbing up a ladder. For this ladder on the left, we can get to the first rung, but there's so much space between the next rung that we know we can't get from one rung to the next. In the second example, the rungs are spaced together nice and close, but we can't even make it to the first rung, so we can't climb up either of these first two. However, in this third example, we can get to the first rung, and each rung is spaced apart nicely, so we could climb this ladder. In order to do a math induction proof, it should look like this third example rather than the first two. And here's our first example. We want to show that n squared plus n is even for any positive integer. So the first positive integer is 1, so we plug 1 in for n. 1 squared plus 1 equals 2. 2 is even, so check that one works. The next step is the inductive step. We want to show that we can go from one rung of the ladder to the next. First step is we are going to assume that it works for some value. So since the formula has n in it, we're going to say, how about some value k? So assume that k squared plus k is even. In other words, we're going to say that k squared plus k is equal to some even value. So 2, where m is any value, and then that means that 2m has got to be even. So then we're going to prove that k plus 1 squared plus k plus 1 is even. In other words, we're taking what we're trying to show, we're plugging k plus 1 in for this n as well as that n. So we want to prove that this is even. Now, if we multiply this out, we would get k squared plus 2k plus 1 plus k plus 1. Now, if we rearrange these a little bit and look to the left, we're going to take this k squared and we can take that k, put them together. So k squared plus k. And then the remaining terms, 2k plus 1 is 2k plus 2. Again, we're just rearranging these things, and we're rearranging them for a good reason, because I know from the earlier assumption that k squared plus k is an even value. It's equal to this 2m. So we're going to put 2m in there. We know this is something that's even, plus, and then we still have this 2k plus 2. Now, we know that something is even if 2 will go into it evenly. So as I look at what this k plus 1 squared plus k plus 1, if we look at what this actually multiplies out to, we're all the way down to here. And all three of those terms, we can factor out this 2. So 2 parentheses m plus k plus 1. And since we can factor a 2 out of them, we know that this must be even. In conclusion, we can conclude the formula is valid not just for 1 or even n, it's for any value of k. So it's formula for all n. All right, next value. We want to prove that 1 plus 3 plus 5 plus 2n plus 1. So this is an arithmetic series. This represents the nth term. We want to prove that this sums up to n squared. First of all, we'll do the basis step. We'll plug 1 in. So 2 times 1 minus 1, does that equal 1 squared? In other words, I'm plugging 1 in for this n and 1 in for that n. 1 is going to be the first term, so 1 on the left, 1 on the right. It works for the first value. So we can get to the first rung of the ladder. Takes us to the inductive step. We're going to assume that 1 plus 3 plus 5 plus dot, 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 plus. Now we're going to plug k into that formula, 2k minus 1. And that would be equal then to, on the right, k squared. So this is our assumption. We're saying, okay, you can get to the first rung, but if you get to any rung on the ladder, can you get to the one that follows it? So we're trying to prove that 1 plus 3 plus 5 plus, we got all the way up to this 2k minus 1. And then the term that would come after that, this is the first term, the second term, the third term, this is the k term. So the term that comes after that would be the k plus 1 term. Right? First, second, third, the k term. If we plug k plus 1 in this expression, we have 2, k plus 1 minus 1, and that's supposed to be equal to, on the right, we don't plug in k, we plug in now k plus 1 squared. So we took this formula from the left, we added the next term, the k plus 1 term onto the left, and it should be equal to k plus 1 squared. Now, simplifying this right side just a little bit, we'll keep it as 1 plus 3 plus 5. I could write a bunch of those terms, although it isn't necessary. We get up to this 2k minus 1 plus, and if we multiply this out, that's 2k plus 2, distribute the 2k plus 2 minus 1, that makes it become 2k plus 1. And on the right-hand side, we're going to square out this k plus 1 squared. That's k squared plus 2k plus 1 once you square all that together. And here's the nice part. We assumed that this was true. We made that assumption. So we're going to plug it in over here. The left side of the equation is all of this. That's the left side of this equation. So what we can do is make this substitution and call that k squared. Right? So we made the assumption already that this was all equal to that k squared. So we're going to use that assumption, plug it in. Plus 2 plus 1 equals right side. We're not changing at all. And as we compare the left side to the right side, they're exactly the same. So we can conclude now the formula is valid not just for k, but for all values of n. Next example, we want to prove this. So the first step is we're going to plug 1 in on the left. We're going to plug 1 in for n on the right. And let's see, 1 on the left, 1 plus 1 is 2, times 1 divided by 2, that's 1, so the basis step works. Now we're into the inductive step. Assume that 1 plus 2 plus 3 plus all the way up to, let's go ahead and plug k in, and we're going to assume it works for the first k terms. So that would be equal to k plus 1 over 2. And then we want to prove, get to the k term, will the k plus 1 term work? So we're going to try to prove that 1 plus 2 plus 3, and what comes after k but k plus 1? So we add k plus 1 onto the left side of this, and on the right, we're going to change, back to this formula, anywhere we see an n, we're going to plug in k plus 1 and k plus 1. So k plus 1, k plus 1, plus 1 all over 2. And we're taking this expression here and plugging k plus 1 anywhere we see the n. And add time to do a little bit of algebra. On the left, 1 plus 2 plus 3 plus k plus 1. We're not going to change that just yet. On the right-hand side, maybe a little bit of work off to the side might be good. K plus 1 times, that's really k plus 2 when we combine like terms. And if we multiply all that out, that's k squared, 2k, and 1k, so that makes 3k. And then 1 times 2 is 2, so it's all over 2. Now we'll make this substitution. We assumed that this was equal to k times k plus 1 over 2. So all of this in what we're trying to prove, we can plug in k plus 1 over 2. Again, I took this out and I made that substitution. We'll write other things the same, plus k plus 1 equals k squared plus 3k plus 2 all over 2. Now here's where the algebra needs to be sharp. We want to show the left side equals the right side. On the left-hand side, this first term would be k squared plus k over 2 when we distribute the k. And everything on the right, as well as this term on the left, has a denominator of 2. So we're going to take this k plus 1 and put it over 2. So if we make it like it's over 1, times 2 in the denominator times 2 in the numerator, it becomes 2k plus 2. The right side is the same, so I'm not even going to bother to rewrite that one. But now on the left, since these both have a denominator of 2, we can combine them together. K squared plus 3k plus 2 is k squared plus k plus 2k, and plus 2, it's all over 2. The right-hand side, if I take a look over there, we had over there, they are exactly the same, which is good news. We proved the basis, we made an assumption, and then it worked for the k plus 1 term. So we can conclude the formula is valid, not just for 1 and not just for the k term, but every term after that. So it's valid for all values of n. Fourth example, we're going to do prove that the sum of this arithmetic series is going to sum to this expression. So for the basis, we plug 1 in for our upper bound. 4 times 1 plus 3 is 7. On the right-hand side, that's 5 plus 2. 7 is equal to 5 plus 2, so that works. Then for our inductive step, we're going to assume that it works from 1 to k. So here is our left-hand side. And to make it look like some previous problems we've done, let's go ahead and write this out in another way. So if we plug 1 in, 4 times 1 plus 3 is 7. Then we plug 2 in, 4 times 2 is 8, 8 plus 3 is 11. So those are the first two terms, and then eventually the last one we're going to plug in is k. So the very last term we get is 4k plus 3. That would be equal to 5k plus 2k squared. So it was given to us in sigma form. We could write out a few of the terms like I have here in red, and now it's a lot more like the ones we've seen before. From here, we'll go to our prove step. We want to prove that I is going not from 1 to k, but k plus 1 of the same function is now equal to 5k plus 1 plus 2k plus 1 squared. We're taking this right-hand side and we're plugging in k plus 1 anywhere that we see the n. All right, so what does it mean for us? If we expand the left-hand side out, we get 7 plus 11 plus dot. Eventually, we plug in a bunch of numbers. The very last one is going to be k plus 1, so 4k plus 1 plus 3. So here is the k plus 1 term. The term in front of that would have been k, so 4k plus 3. And there's a bunch of other terms in there. So this is giving us a representation of this sigma actually listing out a bunch of terms. On the right-hand side, we have 5k plus 5 plus 2. Square this, k squared plus 2k plus 1. And then we'll simplify this down a little bit more. 7 plus 11 plus 4k plus 3. When we expand this term out, the k plus 1 term, that's 4k plus 7. And then on the right-hand side, distribute this 2, so that's 2k squared plus 4k plus 2. So lots of algebra right there. The key substitution, again, is realizing that we assumed that all of this was equal to 5k plus 2k squared. So this we should take out and plug in 5k plus 2k squared. And there's this 4k plus 7 on the right. If we combine all these, that's 2k squared plus 9k plus 7. And now comparing, let's see, simplifying things on the left, 2k squared plus 9k plus 7. That is exactly the same thing that we have on the right-hand side, which is great. So we proved that we added the next term, that formula still worked. So we can conclude the formula is valid not just for 1, not just for k, but for all values of n.